The universe has a highest temperature, a limit so extreme that our laws of physics begin to unravel. It's called the Planck temperature, around 1032 Kelvin, so hot that matter, time, and even the fabric of spacetime lose their familiar meaning. It is the heat of the universe's first instant, the threshold beyond which reality itself begins to blur. Tonight, we drift toward that silent frontier, where energy bends space, particles dissolve into pure light, and the early cosmos glowed with unimaginable intensity. If this quiet journey brings you a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps me keep creating these calm explorations for nights like this. Now, we drift into the first segments, soft steps into a universe that once burned brighter than anything we can imagine. Part 1. The temperature. Where physics breaks, what is the Planck temperature? At about 1.41032 Kelvin, reality reaches a threshold where our equations stop agreeing with one another. Quantum mechanics predicts one future, general relativity predicts another, and the universe itself refuses to choose. The Planck temperature isn't just hot, it's the point where heat becomes geometry and where space-time ripples with such violence that distance and duration lose meaning. To understand why this temperature is so important, you first have to understand what temperature truly measures. It isn't just warmth or the way air feels against your skin. Temperature is motion, the speed and energy of particles as they vibrate, collide, and drift through space. The hotter something is, the more violently everything inside it moves. But as you rise higher and higher on the temperature scale, a quiet truth emerges. Eventually, motion becomes so extreme that it stops behaving like motion at all. Energy becomes gravity, vibrations become curvature, and heat becomes something cosmic. If you follow that path upward, past the temperature of the sun's core, past supernova explosions, past the surface of neutron stars, you reach a realm where ordinary descriptions fail. Even the hottest places we know, regions where matter is crushed into densities far beyond steel or stone, fall billions upon billions of degrees short of the Planck temperature. It is not a temperature found in stars or galaxies. It is a temperature belonging only to the earliest universe, the first sliver of time after the Big Bang. To see why this boundary matters, imagine shrinking your focus down to a region of space so small it could rest on the tip of a proton. Now, imagine injecting enough energy into that region to raise its temperature by 1 degree, then another, then a trillion more. At first, the region simply grows hotter and more chaotic. But as you push past certain thresholds, something deeper happens. According to Einstein's equations, energy is mass, and mass curves spacetime. So the more energy you pack into a tiny volume, the more that region begins to distort the space around it. Eventually, at the Planck temperature, the curvature becomes so extreme that the fabric of spacetime can no longer remain smooth. It buckles, it flickers, it folds in on itself. This is the temperature at which the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have once been unified. At everyday temperatures, those forces behave separately, each playing its own role in shaping atoms, light, and matter. But near the Planck scale, the distinctions blur. Forces no longer keep their identities. They begin to merge into a single interaction, a relic of the universe's earliest symmetry. And yet, we cannot describe this unity with certainty. Our two great frameworks, general relativity and quantum mechanics, cannot be applied together to this domain. When we try, the mathematics becomes unstable. Infinity appears in places it shouldn't. Probabilities break. Predictions contradict one another. It is as if the universe is telling us that our current theories are incomplete, that we are peering too far into a realm we don't yet have the tools to describe. This is what physicists mean when they say the Planck temperature is where physics breaks. Not because nature breaks, but because our understanding does. At such temperatures, particles no longer behave like the familiar building blocks you carry in your body. They lose their shapes and identities, dissolving into fields of pure energy. The very idea of a particle, something with a position, a momentum, a path, stops being useful. Instead, everything becomes a haze of quantum fluctuations, brief sparkles of existence flickering in a storm of light. Here, the vacuum is not empty. It churns, it boils with virtual particles coming into existence and fading away in unimaginably short fractions of a second. This behavior is always present in the universe, even in the quietest spaces between stars. But at the Planck temperature, it becomes the dominant reality. To visualize this, imagine the surface of a calm lake. On an ordinary day, the water seems smooth, reflecting sky and clouds, but as the wind rises, ripples appear, waves grow, crest, and crash. At the Planck temperature, space-time itself behaves like the lake in a storm, not calm, not continuous, but restless. Physicist John Wheeler described this as quantum foam, a froth of microscopic distortions where space and time are constantly being created and destroyed on scales far too small to imagine. Distance becomes uncertain. Time becomes an approximation. Even causality, the idea that one thing happens before another, grows hazy. In this frothing sea, the universe does not look like a place filled with stars and galaxies. It looks like a swirling blur of raw potential, a roiling mix of everything that would eventually become the cosmos we know. You might imagine that reaching this temperature requires unimaginable violence, but the early universe passed through it effortlessly. When the cosmos was just 1043 seconds old, it was so compact and so energetic that the Planck temperature was simply its natural state. Only when the universe expanded and cooled, falling far below the Planck threshold, could familiar physics take hold. In that cooling, the universe began to choose. Forces separated. Particles formed stable identities. The chaotic foam calmed enough to become spacetime. We owe our entire existence to the fact that the universe cooled away from this extreme heat. But there's a deeper question hidden here. Could the Planck temperature ever be reached again? Could any star, any black hole, any cosmic event recreate conditions so intense? The answer appears to be no. Not because the universe forbids it, but because the universe has expanded so dramatically since those first moments that its energy is now diluted across vast distances. Even the most extreme objects, supernovae, gamma-ray bursts, neutron star mergers, reach only tiny fractions of the Planck temperature. Black holes, ironically, get hotter as they get smaller, but even a black hole the size of a mountain would still fall far short of the Planck scale. In particle accelerators on Earth, we accelerate protons to incredible energies, yet even these colossal machines fall short by factors of a trillion. The Planck temperature is not just high. It is a boundary carved into the equations of reality, unreachable with any technology we can conceive. This limit teaches us something profound. The universe is built with a ceiling. Just as there is a smallest length, the Planck length, and a shortest meaningful time, the Planck time, there is a highest temperature. And at that temperature, our familiar ideas, distance, duration, identity, stop being fundamental truths and become approximations of deeper laws. As we drift through this quiet reflection, one question naturally follows. If heat becomes geometry and energy becomes curvature, what happens to matter itself as we approach this ultimate temperature? And as we continue this calm journey, that is where we go next. Part 2. The first instant after the Big Bang. If you could step into the universe's first trillionth of a trillionth of a trillionth of a second, you would enter a world without atoms, without light as we know it, without even the familiar separation between space and time. Temperatures soared near the Planck limit, and in that furnace, the early cosmos behaved less like a place and more like a storm of raw energy. This moment, often called the Planck era, is the closest physics has come to the edge of knowability. Every theory we have begins to break down here. Every equation that usually guides our understanding starts to flicker with uncertainty. The universe was so young, so compressed, and so unimaginably hot that our familiar laws no longer apply. It wasn't that the cosmos ignored them. It was that the cosmos was not yet made of the ingredients those laws describe. There were no particles, no fields in the form we recognize, no geometry that could be measured, only motion and possibility. Imagine compressing the entire observable universe, not just the stars and galaxies, but the dark matter, the cosmic voids, the ancient background light, into a space smaller than the size of a proton. Then, imagine heating that space to a temperature beyond anything that could ever exist again. That was the universe in its first moment, a place so dense that a teaspoon of it would outweigh mountain ranges, a place so hot that matter could not survive for even the briefest fraction of time. Everything dissolved into a churning sea of pure energy. Inside this storm, quantum fluctuations dominated reality. In every tiny region, minuscule ripples in energy appeared spontaneously, then vanished again. These fluctuations were not rare. They were the entire theater of existence. They rose and fell faster than thought, swirling in a pattern so chaotic it resembled the surface of boiling water. But unlike water, the thing that was boiling was space-time itself. Distance had no meaning yet. Time had no rhythm. Without stable particles to mark motion or interactions to define order, everything that existed was suspended in a kind of quantum haze. Events happened, but the word event barely applies. Before and after blended together. Nothing had a position for long, nothing stayed still, nothing remained anything for more than the tiniest flicker. And yet, within this chaos lay the seeds of everything that would come. The early universe was unstable, an immense storehouse of energy ready to unfold, transform, and expand. Tiny variations in its fabric, those quantum fluctuations, were destined to become the structure of the cosmos. These imperceptible ripples would eventually grow into galaxies, stars, planets, and the atoms in your bloodstream. But in the Planck era, they were nothing more than fleeting tremors in a universe too hot and too dense to hold form. If you try to imagine light in this epoch, we must be careful. The light we know, waves of energy moving through space, did not exist. There was no through for it to move. Without space in a stable form, photons had no meaning. Instead, there was only radiation in the loosest possible sense, raw energy without identity, without wavelength, without the gentle oscillation that fills our skies today. In this environment, the four forces of nature were not separate. Gravity, so feeble in our current universe, was as strong as the other fundamental forces. They all blended into one unified interaction, one master force governing everything. This unity is suspected, but still not fully understood. It's a place where theories like string theory and loop quantum gravity hope to provide answers. But for now, it remains an unsolved frontier, a whispered truth rather than a proven one. If you could place yourself inside the first instant, you would not see or hear anything. But you would sense turbulence, not like wind, not like flame, but like the endless folding of something too energetic to stay still. Regions of space would bend inward, others would stretch and twist. Gravity would not pull downward or upward, it would seethe. It would churn with the same restlessness as the energy around it. Then, something extraordinary happened. In less time than it takes light to cross the width of a single atom, the universe began to expand. At first, this expansion was modest, chaotic, uneven, but as it crossed certain energy thresholds, the expansion shifted into a new mode, a rapid, explosive growth known as cosmic inflation. It was a transformation so sudden and so dramatic that the size of the universe doubled again and again and again at unimaginable speed, smoothing the violent quantum froth into something calmer, flatter, and more stable. This transition from the Planck era into inflation marks one of the most significant turning points in the history of existence. Before inflation, the universe was too hot and too distorted for structure to form. After inflation, the cosmic fabric stretched enough that geometry could cool and settle. The randomness of the earliest moment was stretched, diluted, and laid across vast distances. Imagine taking a sheet of paper filled with microscopic wrinkles, then pulling on its edges until those wrinkles become faint, gentle, almost invisible. The early universe underwent something similar. Inflation smoothed the chaos. It took the violent fluctuations of the Planck era and expanded them across cosmic scales, preserving their patterns while calming their intensity. The universe cooled, rapidly, but not instantly. After inflation, temperatures were still staggeringly high, but they were no longer at the impossible Planck threshold. Space could hold particles now. Time could flow in an orderly sequence. Energy could condense into forms that would eventually become the building blocks of atoms. Every step the universe took after this moment was shaped by what happened before it. When forces separated, gravity first, then the strong force, then the electro-weak force, they imprinted new rules into the cosmos. When particles formed, quarks, electrons, neutrinos, they carried the slight irregularities born in the Planck era. These irregularities would set the stage for everything from the clustering of galaxies to the shape of the cosmic microwave background. But the deeper truth is quieter and more humbling. No one has ever observed the Planck era directly. No telescope can see it. No particle accelerator can recreate it. The earliest light we can detect, the cosmic microwave background, comes from a time hundreds of thousands of years after this moment. The Planck era lies behind a curtain that physics has not yet figured out how to lift. And yet, we infer its existence from everything that followed, from the arrangement of galaxies across the sky, from the faint ripples embedded in the cosmic background glow, from the behavior of particles in high-energy collisions, from the mathematics of relativity and quantum theory pointing toward a boundary where they must meet. The first instant after the Big Bang is not simply a point in time, it is the foundation upon which every second of cosmic history rests. It is the heat that became matter, the chaos that became order, the foam that became space-time. And though it lasted for only the briefest sliver of time, it left behind patterns written into the universe on scales so vast they span billions of light years. As we drift deeper into this quiet exploration, one question gently rises. What happens to matter itself in this landscape of unimaginable heat? And that is where our next journey begins. Part 3. When matter ceases to exist. At ordinary temperatures, matter clings together through forces and fields. But near the Planck temperature, those bonds evaporate. Protons dissolve, quarks lose identity, and particles flicker in and out of existence too quickly to form anything stable. Here, matter becomes a brief suggestion, a momentary pattern in a sea of pure heat. To understand this transformation, we must first recall what matter really is. In your everyday world, matter feels solid and dependable. Your hands, the air, the ground beneath your feet, all of it seems built from particles that hold their shape. But on the smallest scales, matter is a dance of fields, forces, and probabilities. Protons are not tiny marbles. Quarks are not miniature spheres. They are excitations in quantum fields, held together by the strong force, their identity maintained by the delicate balance of energy and interaction. As long as the temperature remains moderate, by cosmic standards, these structures endure. The forces that bind quarks inside protons, the electromagnetic fields that hold electrons around atoms, the patterns that make molecules possible, all of them remain stable because thermal motion is limited. Heat shakes matter, but it does not tear it apart. Near the Planck temperature, this balance collapses. Heat, at its core, is motion, particles vibrating, colliding, accelerating. As temperature rises, these motions intensify. Molecules break apart into atoms, atoms break apart into nuclei and electrons. Increase the temperature further, into the millions or billions of degrees, and nuclei themselves break apart into individual protons and neutrons. Push the temperature upward still, and even these building blocks begin to disintegrate. But the Planck temperature lies far beyond these familiar thresholds. Here, the collisions between particles are so violent that any attempt to form a stable structure is immediately undone. If a quark and an antiquark momentarily bind, another collision instantly tears them apart. If a proton begins to coalesce, the surrounding energy shatters it. This is not just disruption, it is complete erasure of persistence. Nothing holds its form for long enough to be called matter. At this scale, the universe no longer behaves like a collection of particles at all. Instead, everything behaves like pure radiation. an ocean of energy where particles are short-lived ripples, nothing more. Their paths, masses, and identities flicker so rapidly that they become indistinguishable from the background heat itself. In such conditions, the strong nuclear force, the glue that holds quarks together, cannot function. It relies on the relative calm of lower temperatures to maintain its grip. But when the surrounding energy is overwhelming, the force cannot compete. Quarks roam freely in a state physicists sometimes call a quark-gluon plasma, though even this term is an understatement at the Planck scale. That plasma, created in modern particle accelerators for the briefest instance, appears only at temperatures trillions of degrees, still far below the Planck domain. Near the Planck temperature, even the idea of a quark as a distinct object begins to fail. Quantum mechanics tells us that particles are defined by the patterns of their fields, by the vibrations and rhythms that distinguish one type of particle from another. But extreme heat disrupts these rhythms. The fields fluctuate too intensely to maintain stable patterns. The tone of a quark, the frequency that defines an electron, the texture that marks a proton, all of these notes are drowned out by the roaring background. Instead of particles, the universe becomes a blur, a storm of interactions where energy dominates over form. Think of a snowflake drifting in calm air. Its structure holds, its beauty persists. Heat that air, and the snowflake collapses into water. Heat it further, and water turns to vapor. But if you heat it enough, far enough, the molecules themselves split. The atoms split, the nucleus splits. Eventually, even the protons melt into something less defined. Now, imagine a heat so immense that even these fragments dissolve beyond recognition. That is the Planck regime. Matter melts not into liquid or gas or plasma, but into something more fundamental. Into pure uncertainty. With so much energy in every microscopic region, spacetime itself becomes unstable. Gravity, electromagnetism, and the nuclear forces stop acting as separate interactions. They merge into something unified, something our present-day physics does not yet fully describe. In this merged state, the usual distinctions between particles blur entirely. Without forces acting in familiar ways, particles cannot retain shape or persistent identity. This is what it means for matter to cease to exist. Imagine a world where an electron, instead of being a distinct particle with a clear mass and charge, is merely a ripple that arises briefly, then disappears, then reappears elsewhere, its nature rewritten by the violent energy surrounding it. Imagine quarks unable to form protons, unable even to maintain their type, flickering between possibilities. Imagine fields so agitated that they overlap into one another, losing the boundaries that define matter and non-matter. This is not emptiness. It is fullness beyond form. And yet, despite this chaos, the seeds of matter are present, because embedded in this storm of heat are tiny asymmetries, slight preferences in how particles flicker. These preferences emerge naturally from quantum fluctuations. As the universe cools, they become amplified. They dictate which particles will survive once temperature falls. They determine how matter will reassemble itself. They inform the structure of atoms, stars, and galaxies. Matter does not vanish permanently in the Planck regime. It merely waits. This waiting is not deliberate. It is structural. When the universe expands and cools, the turbulence softens. Particles remain intact for longer intervals. Interactions stabilize. The storm quiets into something manageable. Quarks settle into protons and neutrons. Electrons orbit newly formed nuclei. Atoms appear. Light gains its familiar wavelengths. Eventually, stars ignite. The universe evolves from a place where matter cannot exist into a place where matter becomes the foundation of everything. But the memory of the Planck temperature never entirely disappears. It lingers quietly in the laws of physics, in the fact that particles have certain masses and not others, in the ratios of matter to radiation, in the subtle ripples of the cosmic microwave background, faint echoes of a time when everything was too hot to hold shape. The universe today is calm by comparison. Structures endure, atoms persist, matter behaves predictably. But the Planck era reminds us that this stability is a product of cosmic cooling, a slow passage from chaos into order. And as we drift further into this quiet exploration, one question rises gently from this transformation. If matter dissolves at the Planck temperature, what happens to space itself under such extreme heat? In the next part, we turn toward spacetime and watch it tremble under conditions that rewrite the geometry of the universe. Part 4. Spacetime under stress. When heat warps geometry. Extreme heat is extreme energy, and extreme energy curves spacetime. At the Planck temperature, the curvature becomes so intense that space itself trembles. Distances fluctuate, angles twist, and the concept of a straight line dissolves into quantum uncertainty. It is a realm where geometry behaves like weather. To understand why this happens, we must begin with a quiet truth from Einstein's general relativity. Space and time are not empty backgrounds. They are dynamic, flexible, and profoundly sensitive to energy. Every particle, every beam of light, every ripple of radiation deforms the fabric of the universe, even if only by the smallest amount. Most of the time, these deformations are so subtle that we never notice them. Even the immense gravitational pull of the sun curves spacetime only enough to gently bend the path of starlight or guide the Earth in its orbit. But as temperature rises, and with it the density of energy, this curvature grows. Heat becomes pressure. Pressure becomes gravity. Gravity becomes geometry. At ordinary temperatures, this influence is imperceptible. Heating a pot of water does not noticeably bend spacetime. But at cosmic scales, energy can accumulate into forms so intense that they distort the universe around them. In a supernova, collapsing matter curves spacetime more sharply. Near a black hole, curvature becomes so strong that not even light can escape its grasp. Yet, even these extremes fall unfathomably short of what occurs near the Planck temperature. At that threshold, spacetime, usually smooth and continuous, begins to behave like a fluid under stress. Instead of stretching gently, it ripples violently. It wavers between expansion and contraction. The very grid of geometry, the invisible lattice that defines near and far, buckles beneath an overwhelming surge of energy. It becomes difficult to talk about distances at all. If you tried to measure the space between 2 points, the answer would flicker unpredictably. One moment the points might appear close, the next, impossibly far. This is because the geometry connecting them is no longer stable. It is quivering like the surface of a lake struck by a sudden storm. In this regime, the classical idea of a straight line, a geodesic in space-time, breaks down. Under normal circumstances, a straight line is simply the shortest path between 2 points. It is the route light follows as it travels through a vacuum. But near the Planck temperature, these paths no longer exist in fixed form. They twist, fragment, and dissolve. Light, if it could exist meaningfully in such a place, would not travel smoothly. Its direction would jitter, its path would swirl, it might veer unpredictably as the geometry around it warps in rapid, chaotic waves. But even this description falls short, because light itself cannot be cleanly defined at these temperatures. It is not a beam. It is a flicker, a breath, a blurred suggestion of its more familiar self. This dissolution of geometry is not a failure of the universe. It is a consequence of quantum mechanics intruding on the structure of spacetime. Normally, quantum effects are confined to tiny scales, atoms, particles, probabilities. But at the Planck temperature, these effects become large enough to reshape the very fabric of reality. Imagine holding a sheet of rubber stretched tightly between your hands. Under a gentle force, it bends predictably. Under a stronger force, it stretches further, but still maintains its integrity. Now imagine shaking it so violently that its surface becomes a blur of motion, its texture distorting faster than you can follow. That trembling is a faint analogy to how spacetime behaves under Planck scale heat. Quantum mechanics insists that energy, position, and momentum are never perfectly smooth or certain. There are fluctuations everywhere, tiny, constant, usually irrelevant. But near the Planck temperature, these fluctuations grow to dominate everything. Spacetime becomes a patchwork of rapidly shifting curvatures. Tiny whirlpools form and vanish. Little pockets of expansion erupt and collapse. The universe becomes a storm of geometry. This is often described as quantum foam, a vivid term coined to capture the essence of this turbulent landscape. In quantum foam, the smooth, gentle geometry of the universe gives way to something more like a frothing ocean, capricious, unpredictable, and endlessly changing. What we call space is not a canvas stretched flat, but a seething medium, constantly rewriting its own shape. In such conditions, the familiar separation between space and time blurs. Distances fluctuate, but so do durations. A second has no stable length. An instant may expand or contract depending on the local curvature. The idea that time flows steadily, that events line up neatly one after another, no longer applies. You could not stand in this environment. You could not observe it. You could not even exist in the way you do now. There is no reference point, no fixed surface, no stillness. Everything is movement, distortion, unfolding geometry. And yet, from within this chaos, deeper laws may be hiding. Physicists suspect that at the Planck scale, space-time is not continuous, but composed of tiny discrete units, quantized chunks of area and volume. These are unimaginably small, far beyond the reach of any microscope or particle accelerator. But near the Planck temperature, they may reveal themselves as the fundamental pixels of reality. If this is true, then the turbulent foam is not simply disorder. It is the restless interaction of the smallest building blocks of existence. In this picture, geometry behaves like weather, because it is built from countless microscopic components responding to extreme conditions. Just as air currents create storms and storms shape clouds, quantum fluctuations at the Planck scale create waves and swirls that ripple across space-time. The universe becomes meteorology of geometry, a storm system without atmosphere, a turbulence of being rather than air. As the universe expands and cools, this storm quiets. Distortions settle. The quantum foam relaxes enough that smooth space-time emerges as an average behavior, like ocean waves calming after a storm. Geometry becomes predictable. Distances become stable. Time flows in a consistent direction. The universe becomes navigable, measurable, and eventually hospitable to matter and light. But the memory of this early turbulence never fully fades. It is preserved in the cosmic microwave background, in the distribution of galaxies across the sky, in the tiny asymmetries that shaped stars and clusters. The quiet order we live within today carries the imprint of a time when space-time itself was wild. And as you breathe now, here, in a universe cooled far below the Planck temperature, you exist inside geometry that has settled into calm. Space is smooth, time is steady. The storm passed billions of years ago. But the question remains, if geometry becomes so chaotic at the Planck scale, then how did the universe ever learn to smooth itself into the calm, vast cosmos we know? In the next part, we drift into the heart of that mystery, toward the birth of quantum foam and the earliest hints of order emerging from chaos. Part 5. The birth of quantum foam. At these impossible temperatures, space-time does not sit still. It bubbles, it flickers, it churns like a restless sea of microscopic fluctuations. Physicist John Wheeler called this state quantum foam, a ceaseless boiling of space-time itself, where the boundary between somewhere and nowhere becomes thin and fragile. To enter this realm, even in imagination, is to step past the edge of familiarity. Our everyday experience teaches us that space is steady, floors remain flat, distances remain constant. If you set an object down, it stays where you placed it. But these certainties exist only because the universe has cooled and expanded enough to make them possible. Beneath that calm surface lies a deeper truth. Space-time is not smooth. It only appears that way from afar. At the Planck temperature, this hidden texture rises into full view. Geometry flickers so rapidly that no point in space remains fixed for more than a fleeting instant. You could not place a marker on a location, because location exists only momentarily before dissolving into a new configuration. The coordinates of the universe rewrite themselves continuously, like a map constantly redrawn while you try to read it. Quantum mechanics predicts that every field, every type of energy, experiences fluctuations even in a perfect vacuum. These fluctuations are usually tiny, too small to disrupt the large-scale structure of space. But as temperature approaches the Planck scale, the fluctuations become energetic enough to twist and fold spacetime itself. The vacuum, instead of being emptiness, becomes a landscape of surging waves and boiling distortions. John Wheeler imagined this foam as a kind of substructure beneath reality, a domain where space is granular and time is intermittent. Not like a solid block, but like something closer to froth. Tiny bubbles rise, expand, and collapse. Short-lived wormholes appear and vanish. Microscopic black holes flicker into being, then evaporate instantly under the immense surrounding pressure. Everything is in motion, everything is unstable. But this bubbling is not random in a careless sense. It is driven by the laws of quantum mechanics, which demand uncertainty in even the calmest circumstances. Position, momentum, energy, even the shape of spacetime cannot be perfectly known. Where there is uncertainty, there are fluctuations. And where fluctuations become unbearably large, they reshape the nature of reality. Think of the ocean from far above. From an airplane window, the surface looks smooth, undisturbed. Only when you descend closer do the waves reveal themselves, ridges, troughs, spirals of foam swirling and collapsing. In the same way, spacetime at human scales appears flat and orderly. But zoomed down by unimaginable factors, billions of billions, and that calm surface dissolves into something wild. At the Planck scale, the fluctuations are so violent that they can briefly tear tiny holes in spacetime. These holes are not tunnels you could travel through. They are far too small, far too brief. But they are evidence that the structure of the universe is not static. It is alive with possibility. Regions of space may pinch closed like soap bubbles. Others may stretch apart. Tiny bridges may form between distant points before snapping back into oblivion. This churning soup of microstructure is what theoretical physicists believe might be the true foundation of spacetime. Instead of thinking of space as a continuous fabric, we can imagine it woven from tiny, discrete building blocks, units of area and volume that flicker between existence and non-existence. The foam is not a surface atop something deeper. It is the deeper layer, the bedrock beneath geometry. The birth of quantum foam is tied to the early universe, but the foam did not vanish when things cooled. It simply quieted. Even now, at every point in space, fluctuations continue. They are just much smaller than the wavelengths of light or the paths of particles. The smooth geometry we experience is an average over the chaotic motions beneath. Like waves on a calm sea, the foam is always present, always shifting, but usually hidden from our senses. The idea that spacetime is not continuous but granular is supported by several approaches in physics. Loop quantum gravity, for instance, proposes that area and volume come in discrete units, quanta of geometry. In that picture, the foam reflects the jittering of these geometric grains at high energy. String theory imagines that the fundamental components of the universe are vibrating strings or loops, and these vibrations ripple through spacetime, creating its structure. In that view, quantum foam arises from the collisions and interactions of these strings at extremely high energies. Although we cannot directly observe the foam, its fingerprints may be present in the cosmic microwave background or in the patterns of gravitational waves that ripple across the cosmos. Some physicists speculate that tiny distortions in the propagation of light over billions of years could reveal the graininess of space. But so far, the evidence remains subtle and indirect. Why does the universe foam at all? Why does spacetime refuse to stay still? The answer lies in the impossibility of perfect emptiness. According to the uncertainty principle, energy cannot be exactly zero. Even in a vacuum with no particles, fields must fluctuate. These fluctuations give rise to pairs of virtual particles, tiny flashes of existence that borrow energy from the vacuum, then disappear before the universe notices their debt. At low temperatures, these flickers are faint. At the Planck temperature, they burst into prominence. Each fluctuation disturbs the geometry around it. Gravity responds to energy, and fluctuations are bursts of energy. Thus, each quantum tremor curves spacetime, which then reacts, causing further fluctuations. Geometry and energy feed into each other in a feedback loop so rapid that the distinction between them becomes blurred. Is the foam the result of energy fluctuations, or are the fluctuations the result of curved geometry? At the Planck scale, the question has no single answer. They arise together, inseparable. To see the foam as it first emerged, imagine the universe in its earliest moment. Temperature was so high that the energy density approached infinity. Every point in the cosmos was violently unstable. Space itself was so compact that these fluctuations collided constantly, fusing into larger distortions. There was no uniform direction, no sense of up or down, only the swirling turbulence of an infant spacetime struggling to form. This is the birthplace of geometry. As the universe expanded, the foam stretched, the bubbles lengthened, the fluctuations smoothed. Regions that once folded and twisted became vast and nearly flat. The storm calmed just enough for quantum foam to shrink to scales far beyond detection. What remained was the foundation of spacetime, a smooth geometry built upon a restless microscopic world. Today, the foam is quiet. It bubbles beneath the surface of every volume of space, but softly, like whispers beneath a symphony. We move through it without noticing. Photons glide through it without scattering. Time flows despite its trembling base. The foam is not gone. It is simply small, subdued by the cooling and expansion of the cosmos. But the idea of quantum foam reminds us of something profound. Smoothness is an illusion born from distance. Order emerges from chaos. The stability of your world rests upon a foundation that once churned so violently it barely qualified as space at all. And as we prepare to drift deeper into this cosmic landscape, another question rises gently from the foam itself. If the universe began in this restless, boiling state, how did it develop rules, laws of physics that remain so stable today? In the next part, we explore that quiet puzzle, the universal boundary of heat. Part 6. Why heat has a limit. It may seem strange that temperature, which can always rise in everyday life, suddenly stops at a boundary. But the Planck temperature emerges from combining the constants of nature, light's speed, Planck's constant, and gravity's strength, into a single limit. Beyond this point, heat injects so much energy into so small a space that space-time collapses under the weight. To understand why heat has a maximum, we must first understand what heat truly represents. In daily life, temperature feels ordinary. Warm air on your skin, coffee cooling beside you, sunlight softening as evening approaches. But beneath those sensations lies a deeper truth. Temperature is motion. It is the average energy of countless particles vibrating, bouncing, and colliding in perpetual dance. At low temperatures, these motions are gentle. Molecules drift slowly, electrons swirl quietly, raise the temperature, and everything quickens. The atoms in a metal rod vibrate more intensely. A gas expands as its molecules push outward. Thermal energy is motion made manifest, but motion does not increase indefinitely. At some point, it reaches a threshold where adding energy no longer changes the behavior of matter in familiar ways. Instead, the energy becomes so concentrated that it begins altering the structure of space-time itself. This boundary, the Planck temperature, is not an arbitrary cutoff. It arises naturally from the three fundamental constants that govern the universe. The speed of light, c, which sets the fastest motion anything can achieve, Planck's constant, h, which sets the scale of quantum effects, and Newton's gravitational constant, e.g., which determines how strongly mass and energy curve spacetime. When combined through dimensional analysis, these constants yield a temperature so vast, so extreme, that it marks the point where classical concepts break down. It is not merely a limit of technology or imagination. It is a limit written into the fabric of nature. Why? Because past this point, temperature no longer describes motion of particles. There are no particles left to move. their identity dissolves into the chaos of quantum gravity. Imagine heating something, a gas, a star, a cloud of plasma. At first, the added energy simply increases the speed of the particles inside. But as temperature rises, collisions become more violent. Eventually, atoms break apart into electrons and nuclei. Push further, and nuclei disintegrate into quarks and gluons. Heat even more, and these too begin to lose stable identity. Now imagine continuing to increase the temperature. Increase it until every vibration, every quantum state, every fluctuation becomes so intense that the energy density in the region is enough to form a miniature black hole. At this threshold, the effort to probe smaller distances simply collapses the region into gravitational darkness. This is the heart of the limit. If you try to make temperature increase, you must pack more and more energy into smaller and smaller volumes. But the moment you pack enough, gravity responds. Space curves inward, a horizon forms, and the energy you were trying to use to heat the system is now trapped behind the gravitational boundary. In other words, temperature cannot rise beyond the Planck scale because the very act of trying to exceed it destroys the system that would contain it. It is as if the universe is saying, this far and no further. Heat encounters a wall, not because nature refuses to get hotter, but because hotter states no longer have meaning within the framework of spacetime. There is a subtle elegance in this. The constants of the universe converge to set a physical boundary, a ceiling beyond which our familiar descriptions of reality falter. Temperature, which feels like a simple measure of warmth, is ultimately constrained by the geometry of the universe. To appreciate the limit more deeply, imagine trying to see the smallest details in nature using shorter and shorter wavelengths of light. At ordinary scales, this works beautifully. Microscopes use light to examine cells. Electron microscopes use even shorter wavelengths to reveal atoms. Particle accelerators smash particles together to probe deeper still. Each increase in resolution demands higher energy. But at the Planck scale, the strategy fails. When you focus too much energy into a tiny spot, the spot collapses under its own gravitational field. The smaller you try to look, the less you can see, until vision itself is swallowed by curvature. Temperature follows the same principle. To make something hotter, you compress more energy into a smaller space, but compress too much, and gravity takes over. This limit reveals something profound about the relationship between energy and geometry. They are not separate domains. Energy shapes geometry. Geometry shapes energy. At low temperatures, this relationship is gentle. At high temperatures, it becomes inescapable. Beyond the Planck temperature, space-time becomes so unstable that it can no longer provide a meaningful stage for physics to unfold. Distances cease to have consistent length. Durations cease to have reliable flow. Fields jitter so wildly that their average values lose meaning. The universe enters a regime where our equations, general relativity, quantum mechanics, can no longer accurately describe what is happening. This is not a failure of nature. It is a failure of our theoretical tools. Nature continues to evolve smoothly, but our understanding does not. In this sense, the Planck temperature is more than a boundary. It is a clue. It hints that at the deepest level, space-time is not a continuous surface. It suggests that beyond this limit lies a more fundamental layer of physics waiting to be discovered, perhaps quantum gravity, perhaps strings, perhaps something entirely different. Many theories propose that at the Planck temperature, space-time becomes granular, composed of tiny indivisible units of area and volume. Others suggest the universe transitions into a state where dimensions behave differently, where space loses meaning and time becomes a quantum variable rather than a flow. Whatever the truth, the Planck temperature marks the doorway. It separates the universe we inhabit, calm, structured, predictable, from the universe that existed in the first instant after the Big Bang, where everything was too hot and too energetic for structure to survive. As the early cosmos cooled, it crossed down through this threshold. Only then could space-time stabilize. Only then could forces separate into their familiar forms. Only then could particles gain identities and persist long enough to form atoms. Here lies the quiet miracle. The universe moved from a place where heat had no upper bound, where spacetime was a storm of geometry, into a place where temperature could vary meaningfully at all. Without crossing below the Planck temperature, the universe could never have developed stars, planets, chemistry, or life. Heat has a limit, because heat is not just a property of matter, it is a property of the universe itself. And as we rest within a cosmos comfortably far below that boundary, a gentle question emerges. If heat has a ceiling, what happens to the particles that carry energy when the universe becomes so hot they cannot survive? In the next part, we drift into that frontier, toward light itself and its unique ability to remain when matter falls away. Part 7. When light becomes the only form of matter. In the early universe, when temperatures hovered near the Planck scale, particles and antiparticles formed and vanished faster than thought. The only truly stable inhabitant of that era was light. Not the gentle glow we know, but an ocean of radiation so intense that it alone defined the structure of everything. To imagine this state, you must let go of nearly every intuition about light you carry from everyday life. The light we know, sunlight drifting through atmosphere, lamplight softening a room, starlight crossing millions of miles, is a delicate, familiar presence. It illuminates the world without disturbing it. It is gentle, almost weightless. But light in the early universe was nothing like this. It was the dominant force, the primary architecture of reality, the scaffolding around which the first patterns of space and time formed. At these temperatures, matter could not hold. Atoms could not form. Protons and neutrons could not persist. Even quarks and antiquarks appeared only briefly, flickering in and out like sparks in a storm. Every particle that emerged was annihilated almost instantly by its antiparticle counterpart, releasing more radiation back into the surrounding sea of light. In that churning chaos, the universe was not a place of matter at all. It was radiation embodied. Light, or more precisely, photons, were the only entities capable of maintaining any identity. Unlike massive particles, photons do not rely on structural integrity. They are not built from smaller components. They do not have internal makeup to tear apart. They are disturbances in the electromagnetic field, ripples of pure energy. This makes them uniquely durable in environments too violent for matter. In the early universe, photons were everywhere, not drifting or gliding, but colliding, scattering, merging, and splitting in frantic succession. They flooded every direction. They jostled and compressed the space around them. At these densities, their presence shaped the geometry of the infant cosmos, pushing outward, driving expansion, and setting the stage for what the universe would eventually become. Remember that photons move at the speed of light not by choice, but because they have no rest mass. They cannot slow down. They cannot stop. So in this early epoch, where temperatures soared and distances shifted unpredictably, photons raced endlessly, tracing paths through a geometry too unstable to guide them cleanly. Their trajectories jittered as space-time itself flickered beneath them. Yet through all of this instability, light persisted where matter could not. If you could somehow stand in this universe, though no form of consciousness could survive it, you would not see brightness as you know it. You would not see color. At the Planck temperature, photons carried energies so extreme that their wavelengths were far too short to be interpreted by any biological eyes. This was not visible light. It was something more raw, more fundamental, an ocean of high-energy radiation permeating everything. Photons dominated the universe not just by number, but by influence. They shaped the pressure, density, and behavior of space-time. They pushed the cosmos outward, contributing to the rapid expansion that followed the Big Bang. They dictated how matter, when it finally cooled enough to appear, would distribute itself. Their interactions left subtle imprints that scientists can still detect today in the form of cosmic background patterns. But to understand why light alone could survive, we must return to the nature of temperature. At extreme temperatures, energy is so intense that the distinction between particles and radiation becomes blurred. A photon can vanish, giving rise to a particle-antiparticle pair. A particle-antiparticle pair can annihilate back into radiation. This dance occurred constantly in the young universe. But because photons had no rest mass and no internal structure to break, they persisted through every exchange. Matter, by contrast, is fragile. It requires stability. It needs forces, like the strong nuclear force, to hold it together. These forces cannot function at the Planck scale because they require temperature to fall below certain thresholds to bind particles. Before then, the forces are overwhelmed by energy. Every attempt at structure is torn apart. And so, the earliest universe was not a universe of atoms, but a universe of radiation in its purest form. Interestingly, this early dominance of light is not just a historical curiosity. It plays a crucial role in why the universe has the structure it does today. When radiation rules, it resists compression, it creates outward pressure. In the post-Big Bang environment, this pressure shaped the expansion rate of the cosmos. It smoothed irregularities, it stabilized the foam-like geometry. It spread uneven fluctuations over vast distances, laying the groundwork for cosmic inflation. As the universe expanded and cooled, the relative influence of radiation decreased. Even so, the early reign of light left behind echoes, patterns embedded in the cosmic microwave background, a faint afterglow from when matter finally formed stable atoms hundreds of thousands of years later. These patterns reveal slight fluctuations in density that light itself helped sculpt. They act as fossils of an era when photons governed the cosmos. To appreciate the energy of these ancient photons, consider that the photons we see today as the cosmic microwave background have stretched dramatically due to the expansion of the universe. They are cold by cosmic standards, just a few degrees above absolute zero. But when they first appeared, they were unimaginably hot. They were part of the same radiation ocean that once defined the structure of the cosmos. There is a quiet beauty in this transition. Light, the earliest architect of the universe, gradually ceded control to matter. As temperatures dropped, particles began to survive longer. Quarks formed protons and neutrons. Electrons eventually joined them to form atoms, and only then, hundreds of thousands of years later, could light finally travel freely without constant scattering. The universe moved from a radiation-dominated era to a matter-dominated one. But the memory of its luminous origin never vanished. Even now, light remains deeply woven into the fabric of reality. Photons mediate electromagnetic forces. They carry information across cosmic distances. They illuminate galaxies that formed from the fluctuations they once sculpted. They remain the messengers of the early cosmos. And, in a deeper sense, they carry something else, a reminder that the universe did not begin with the solidity of matter, but with the fluidity of radiation. Light was the first inhabitant, the first structure, the first presence that could survive the overwhelming heat of infancy. In the silence of this reflection, a soft question emerges. If light could endure where matter could not, what does this reveal about the forces that shape the universe? As we continue this quiet exploration, we drift next into the realm of gravity, into the moment when even spacetime's oldest force reached its breaking point under the heat of creation. Part 8. Gravity at its breaking point. At the Planck temperature, gravity becomes as strong as the other forces of nature. The familiar hierarchy, weak nuclear, strong nuclear, electromagnetic, gravitational, begins to blur. It is in this moment that scientists suspect all forces might unify into a single interaction, the oldest and most mysterious dream of physics. Gravity, as we know it, feels gentle. It's the force that lets you walk, the force that keeps oceans pinned to the earth, the force that shapes planets and stars. But compared to the other fundamental forces, gravity is extraordinarily weak. A small magnet can lift a paperclip despite the entire Earth pulling downward. Protons and neutrons cling together far more tightly through the strong nuclear force. Electrons bind to atoms through electromagnetism. Gravity, in our daily world and even in the world of atoms, is almost an afterthought. Yet at the Planck temperature, this quiet force rises to unmatched strength. It stops whispering and begins shouting. The tremors of quantum mechanics intrude into its structure. Space bends, crumples, and rearranges itself under energies so high that gravitational interactions can no longer remain the background stage. They become participants in the chaos. To understand why gravity strengthens, we must look at how energy and spacetime are related. Einstein taught us that mass and energy curve spacetime. The more energy a region contains, the stronger the curvature. At everyday temperatures, this curvature is microscopic, too subtle to detect without sensitive instruments. But near the Planck temperature, where energy density is beyond comprehension, curvature becomes violent. Imagine packing the energy of a star into a volume smaller than the tip of a needle. Imagine that energy fluctuating, twisting, rising and falling in bursts shorter than the Planck time. Gravity responds to this extreme environment not with the slow, predictable pull we know, but with erratic surges, collapses, and expansions. It behaves like a force pressed far beyond its normal range. At this scale, gravitational strength becomes comparable to the strong nuclear force, to electromagnetism, to the weak force. The old hierarchy collapses. Gravity no longer lags behind, it stands as an equal. This equality hints at something profound. Physicists have long suspected that the four forces of nature were once unified in a single interaction. Today, they appear separate because the universe has cooled and expanded. But in the earliest instance, at temperatures near the Planck scale, the differences between forces may have dissolved. The familiar divisions, the strong force holding quarks together, electromagnetism binding atoms, the weak force driving radioactive decay, gravity shaping cosmic structure, may not have existed at all. Instead, there may have been one primordial force, one deep symmetry of nature that fractured as the universe cooled. This breaking of symmetry is believed to have created the diversity of forces we observe today. In this sense, the Planck temperature is not just a limit, it is a doorway into a simpler universe, a universe before forces had identities. At this threshold, gravity's behavior begins to resemble the quantum world. Normally, quantum effects dominate the microscopic realm, electrons whose positions blur into probabilities, photons that act as both waves and particles. Gravity, described by classical geometry, rarely participates in this blur. Its laws remain smooth and continuous. But the Planck scale changes this. Spacetime becomes grainy, jittering with quantum fluctuations. Its curvature shifts so rapidly that the smoothness of Einstein's equations breaks down. We are left with a picture of gravity that is no longer classical. It becomes quantized, broken into discrete packets, responding to the same principles that govern electrons and photons. This is the domain physics has sought for nearly a century, a quantum theory of gravity. Multiple attempts have been made to describe this unification. String theory proposes that the fundamental elements of nature are vibrating strings, and that gravity arises naturally from one of these vibration patterns. Loop quantum gravity suggests spacetime is built from quantized loops, like tiny woven threads forming a vast cosmic tapestry. Other theories imagine extra dimensions, hidden fields, or mathematical symmetries that extend beyond the geometry of our universe. None of these frameworks has yet been confirmed, but they share a common dream, that at the Planck scale, the universe becomes simpler, not more complex. Complexity, protons, atoms, planets, galaxies, comes later as the universe cools and the primordial symmetry fractures. At the Planck temperature, however, symmetry dominates, forces merge. Gravity loses its identity as a gentle sculptor of stars and becomes instead a sharp, dominant interaction, shaping quantum geometry in ways we do not yet fully understand. It is helpful to imagine gravity at these scales not as a force that pulls, but as a property of spacetime that shifts with explosive sensitivity. A tiny quantum fluctuation in energy can produce a surge in curvature, causing regions of spacetime to pinch inward or balloon outward in unpredictable ways. These fluctuations are not confined to large volumes. They occur at the smallest possible scales. Each quantum of spacetime, each grain at the Planck length, can warp, swell, or collapse in response to tiny changes around it. This behavior is far removed from the stable gravity we experience today. At human scales, gravity is a calm and continuous presence. At cosmic scales, it shapes the formation of galaxies over billions of years. But at the Planck temperature, gravity acts more like a turbulent ocean. The gentle curves of space-time transform into frothing waves and swirling eddies, each one forming and dissolving in unimaginably small fractions of a second. It is this turbulence that likely drove the next major event in cosmic history: inflation. When gravity is pushed to its limits, when it can no longer maintain stability, the universe expands in response. A rapid exponential expansion, far faster than the speed of light, smooths out irregularities and cools the universe just enough to leave the Planck era behind. Gravity, in its broken and unstable form, may have triggered this explosive transition. And so, the breaking point of gravity becomes the birthplace of cosmic order. As temperatures fall, the universe stabilizes. The strong force separates from the unified interaction. Then, electromagnetism and the weak force diverge. Gravity begins to soften, retreating from its moment of dominance into the quiet, gentle role it plays today. The forces sort themselves into the hierarchy we observe, each adopting its familiar behavior as the universe continues to cool. But the memory of that early unification remains embedded in the laws of nature. It is the reason the forces share mathematical similarities. It is why particles come in families. It is why the universe exhibits symmetries at deep fundamental levels. The Planck era did not simply precede the familiar universe. It shaped its rules. Even now, every gravitational wave that ripples through space, every particle that decays, every photon that travels across the void is influenced by the structure that emerged from those first instants. Gravity's breaking point was not the end of the universe. It was the beginning of structure. And with this quiet reflection, another question rises gently from the fabric of space-time. If gravity lost its identity during the Planck era, what did the universe look like as it tried to expand through such unimaginable heat? This leads us softly into the next chapter, the moment when expansion itself struggled to make sense in a universe too hot for structure to form. Part 9. A universe too hot for space to expand smoothly. Our universe expanded rapidly after the Big Bang, but during the earliest fraction of a second, its growth was chaotic. At such enormous temperatures, energy density was so high that the fabric of space stretched unevenly. It took cooling, falling far below the Planck temperature, before cosmic inflation smoothed the wrinkles. To understand why the early universe expanded so unpredictably, we must begin with the state of the cosmos at its birth. In the Planck era, space was not the calm, continuous medium we experience today. It was wild, boiling with fluctuations, trembling with quantum foam, and distorted by immense concentrations of energy. Space-time itself behaved like a churning ocean in stormlight, its surface rising and falling in violent, unpredictable waves. In such conditions, expansion could not proceed smoothly. There was no uniform background on which to stretch. Each tiny region of the universe behaved differently. One region might balloon outward while another caved inward. Some areas were dense with energy, others sparse. In places, space-time curled tightly. In others, it flattened. Expansion occurred, but it was a patchwork of surges and collapses rather than a single coherent swelling. This early expansion resembled turbulence more than growth. Imagine heating water in a pot until it boils vigorously. The surface does not rise smoothly. Instead, bubbles erupt unpredictably. Surges push outward, then collapse. That is a faint echo of what space-time experienced in its earliest moments. But the differences are enormous. In this primordial era, boiling happened not in water, but in geometry itself, driven by the energy scales associated with the Planck temperature. Energy so high that gravity, quantum mechanics, and fundamental forces intertwined in ways we cannot yet fully describe. At these extreme temperatures, even the direction and rate of expansion varied moment to moment. Remember that space is not a rigid container. It is a dynamic field shaped entirely by the energy within it. When energy density fluctuates wildly, expansion becomes unpredictable. Where energy was momentarily higher, space-time curved inward more strongly, producing regions that resisted expansion. Where energy dipped, space-time stretched more freely, creating pockets of rapid enlargement. These tiny deviations would eventually seed the large-scale structure of the universe, but in the earliest instance, they made expansion jagged and chaotic. In these conditions, the idea of a smooth beginning is misleading. The universe did not initially expand like a balloon filling with air. It expanded like a balloon made of liquid, its surface trembling and reshaping itself continuously. This chaotic phase was short-lived, astonishingly short-lived. Yet it was long enough to imprint seeds of inhomogeneity into the cosmic fabric. These seeds would later grow into the clusters, filaments, and voids of the universe's large-scale structure. In a sense, the wrinkles of the early cosmos became the scaffolding for everything we see billions of years later. But the universe could not continue in this chaotic state. Without smoothing, the cosmos would never form galaxies. Light would not travel predictably. Regions of space would remain disconnected or unstable. Something needed to happen to iron out the wrinkles. That something was cosmic inflation. Inflation was not gentle, it was not slow. It was not symmetrical in the way expansion feels today. It was an explosive, exponential stretching of space that occurred within a tiny fraction of a second, magnifying the universe by factors far beyond human comprehension. It took the chaotic, boiling geometry of the Planck era and pulled it taut, like stretching crumpled fabric, until it becomes nearly flat. Why did inflation occur? Physicists propose that a special field, the inflaton field, held extremely high potential energy in the early universe. As this field relaxed, its energy drove the rapid expansion. The details are not yet fully understood, but the consequences are unmistakable. Inflation smoothed the uneven energy distribution left behind by the Planck era. It stretched the foam-like distortions until they became minuscule ripples. It made space nearly uniform with only slight variations, tiny differences in density preserved. These variations, expanded to cosmic scales, later guided the formation of stars and galaxies. Without inflation smoothing the early chaos, the universe would look nothing like it does now. It would be fractured, unstable, and likely inhospitable to the emergence of life. But the importance of cooling cannot be understated. Before cooling, inflation could not begin. The Planck temperature represented a threshold where conditions were simply too wild for any coherent expansion. Only once temperatures fell, only once the energy density became more manageable, could inflation take over. In this sense, cooling was the universe preparing its own stage. As the temperature dropped, space-time stopped flickering so violently. Geometry settled enough to allow large-scale patterns to form. Forces began to separate from their unified state. The extreme quantum turbulence of the Planck era faded into the background. The universe became structured enough for inflation to smooth it. In the aftermath of inflation, the universe expanded more gently. Space still stretched, but no longer in chaotic fits and starts. Instead, it grew with astonishing uniformity. This uniformity is visible today in the cosmic microwave background, a faint glow left over from when the universe was only a few 100,000 years old. The temperature differences in that glow are tiny, just millionths of a degree. These tiny variations trace their origins to the quantum fluctuations of the Planck era, stretched across trillions of miles by inflation. In a beautiful symmetry, the chaos of the earliest instance became the blueprint for cosmic structure. The universe did not need perfection to grow orderly. It needed the right kind of imperfection, amplified at the right moment. Still, the idea of a universe too hot for smooth expansion carries a deeper philosophical weight. It reminds us that the early cosmos was not born calm. It was not born organized. It began in turbulence, in unpredictability, in extremes beyond extremes. Order emerged only after cooling, after smoothing, after a transition from unbounded energy to something more stable. And so, the early universe teaches us that smoothness is not the default state. It is an achievement. Today, we inhabit a cosmos where space expands gently, predictably, guided by dark energy. Galaxies drift apart like islands carried by a slow, quiet tide. But beneath that calmness lies a memory, echoes of a time when expansion was a tempest. As we continue this quiet journey backward through cosmic time, a new question arises. How did time itself behave in an era where nothing could expand evenly, where every moment was shaped by turbulence? In the next part, we drift even deeper into that mystery, toward the earliest meaning of time in a universe nearing its maximum heat. Part 10. What happens to time at maximum heat? Time flows because events follow one another in a clear sequence. But near the Planck temperature, that sequence dissolves. Interactions occur so rapidly and energies become so intense that the idea of before and after loses meaning. The clock of the universe blurs into something deeper than duration. To understand how time behaves at these extremes, you must let go of the comforting picture of time you carry with you. Time is a line, time is rhythm, time is something that marches steadily forward no matter what. In your everyday world, time is dependable. Seconds pass, clocks tick, your heartbeat keeps its rhythm. Even in the broader universe, time flows in a fairly orderly way. Stars age, galaxies drift, light travels at its constant speed. But time, at its deepest level, is not guaranteed to behave this way. Time is woven into spacetime, and spacetime itself is sensitive to energy and conditions. When energy becomes unbounded, and when spacetime collapses into chaos, the flow of time becomes unpredictable and almost unrecognizable. Near the Planck temperature, events occur at scales so tiny and energy so high that quantum mechanics and general relativity clash violently. The smooth unfolding of spacetime is replaced by something jagged and uncertain. Instead of moments following one another in clear sequence, interactions pile on top of each other so quickly that they lose individuality. A single Planck time interval is roughly 1043 seconds. It is the smallest meaningful unit of time according to our current understanding. Beneath this threshold, even the notion of duration stops making sense. At normal temperatures, processes unfold in long chains. A particle moves from one position to another. A photon travels from a star to your eye. But at maximum heat, particles flicker in and out of existence before they can traverse the smallest distances. Their paths do not form lines but bursts of probability. Interactions occur not as separate events but as overlapping tremors. The chain breaks, sequence dissolves. It is not that time stops, rather, time loses its direction. It becomes a haze of possibilities, a field of uncertainty, an environment in which causality, the idea that one thing leads to another, begins to unravel. To understand this, imagine a crowd of people walking down a quiet street. Each person has space. Each step is distinct. That is ordinary time. Now, imagine compressing that crowd into a tiny alley, people packed shoulder to shoulder, all trying to move at once. Individual steps lose meaning. Sequence breaks down. That is time near the Planck temperature. Too much happening in too small a space for distinctions to survive. In this regime, the universe does not experience time as flow. Instead, it experiences time as fluctuation, as turbulence. The geometry of time bends, stretches, and warps under the same pressures that distort space. Just as distances become uncertain, durations become unstable. A moment may expand or contract unpredictably. The idea of a moment may not even apply. Einstein taught us that time is relative, that motion and gravity affect its passage. A clock deep in a gravitational well runs more slowly. A fast-moving observer will age more slowly. But at the Planck temperature, this relativity becomes extreme. Gravity is no longer a smooth curvature, but a violent, fluctuating storm. Time, therefore, does not merely slow or speed. It shatters into something without clear shape. Under such conditions, you cannot meaningfully define 1 second. You cannot identify now. You cannot describe sequences because the conditions needed for sequencing, stable spacetime, predictable interactions, do not exist. Time becomes probabilistic, a quantity that flickers like everything else in this extreme domain. The rise of quantum foam, discussed earlier, plays a central role here. In quantum foam, space-time exists as a frothing, boiling medium of fluctuations. These fluctuations warp space, but they also warp time. Tiny loops of space-time can form and collapse. Microscopic wormholes may flicker into existence, connecting regions in ways that violate ordinary notions of causality. In this environment, even the direction of time, its arrow, becomes ambiguous. In your everyday life, the arrow of time points forward because entropy increases, heat spreads, order dissolves into disorder. But entropy is meaningful only when large-scale patterns exist. Near the Planck temperature, those patterns are absent. There is no meaningful distinction between order and disorder, no gradients for entropy to climb. As a result, the arrow of time becomes indistinct. Without structure to decay, time has no direction to follow. This is one of the deepest mysteries of cosmology. If the early universe lacked a clear arrow of time, what caused time to choose a direction as the universe cooled? Some physicists argue that the arrow of time emerges from expansion. As space expands, it creates room for entropy to increase. Others propose that the arrow emerges from symmetry breaking, the divergence of forces, the formation of particles, the onset of structure. Still others suspect time's arrow is a statistical illusion, a feature that arises naturally when a system becomes large enough to behave classically. Whatever the answer, one thing is clear. Time as we understand it could not exist in the earliest universe. The Planck era was not a place where moments followed moments. It was a place where the concept of moment had not yet been born. Instead, there was only change without sequence, motion without path, interaction without chronology. When the universe began expanding through inflation, cooling rapidly and stabilizing its geometry, time regained its footing. The foaming, flickering geometry settled into something usable. Particles stopped overlapping so violently. Forces separated. Structures, however small at first, began to hold their form. The stability allowed processes to unfold in predictable ways. Cause could lead to effect, moments could line up, time flowed again. But its early origin remains a profound reminder that the flow of time is not fundamental. It is emergent. It arises when the universe becomes gentle enough to support sequence. Even now, the echoes of that early instability persist. In the depths of black holes, near singularities, in regions of space-time where energy densities rise to extreme levels, the old behavior returns. Time falters, horizons form, sequences break, physics grows uncertain. These environments remind us that the universe still holds places where the rules of time approach their breaking point. As you breathe in the quiet stability of the present universe, it is astonishing to imagine that the flow of time you rely on, your pulse, your thoughts, your memories, arose only after the cosmos cooled enough to allow it. Time is not a universal truth. It is a gift of order. And as we continue drifting through the cosmic past, another question emerges gently from this reflection. If time itself struggled to exist near the maximum heat, what happened to regions of the universe where heat and gravity combined in extreme ways, regions that would later echo in the form of black holes? The next part takes us there, into the heart of these ancient parallels, where maximum heat and maximum curvature meet. Part 11. Why black holes echo the Planck temperature. Inside a black hole's core, or at least in the equations that describe it, temperature climbs toward the same catastrophic limit. The singularity predicted by general relativity may not be a single point at all. It may instead be a region where conditions match the Planck temperature and space-time folds in on itself. To explore this idea, we must first step gently into what a black hole truly represents. In everyday imagination, a black hole is a place where gravity has become so strong that nothing, not even light, can escape. Space curves inward like a funnel with no bottom. Time slows to a crawl near the edge. But this description, while evocative, barely scratches the surface. A black hole is more than a crushing gravitational well. It is a laboratory of extremes, a place where the laws of physics are stretched to their limits. At the heart of every black hole lies something we call a singularity. In classical general relativity, This singularity is a point of infinite density, infinite curvature, and infinite temperature. But infinities in physics are usually signs not of real physical entities, but of the breakdown of our equations. They signal that the theory we are using cannot describe what actually happens there. Much like the Planck temperature marks the limit of our understanding of heat, the singularity marks the limit of our understanding of gravity. It is here, inside the black hole's center, that nature may recreate the same impossible conditions that existed during the universe's first instant. To see why, imagine falling toward the singularity. At first, gravity pulls you steadily inward, but as you draw closer, the pull intensifies exponentially. The tidal forces, differences in gravitational pull across your body, grow immense. They stretch everything along the direction of the fall and compress everything across it. If you could measure the energy density of the region you approach, you would find it increasing without bound. Distances shrink, time distorts, and the deeper you fall, the hotter the surrounding energy becomes. This rising temperature is not like the heat from a flame or a furnace. It is gravitational heat, a consequence of energy compressed into ever smaller volumes. As you approach the center, the energy density approaches the Planck scale. The curvature of spacetime grows so extreme that quantum effects can no longer be ignored, and the temperature, predicted by the equations of relativity, soars toward the Planck temperature. This eerie similarity is not an accident. Both the early universe and the interior of black holes are regions where gravity becomes strong enough to dominate every other force. In both environments, the curvature of spacetime becomes violent and unpredictable. In both, energy density becomes so high that the smooth geometry of general relativity breaks down. And in both, the physics we know loses its grip, requiring a deeper, unified understanding of quantum gravity. In this sense, a black hole is like a tiny, self-contained echo of the universe's birth, not in the way it formed, but in the conditions that arise inside it. But there is something even more intriguing. Black holes are not just gravitational objects, they are thermodynamic ones. They have temperature, entropy, and energy balances just like any physical system. These thermal properties were first understood in the 1970s through the work of Jacob Bekenstein and Stephen Hawking. Their surprising discovery was that black holes emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. The temperature of a black hole, according to Hawking, depends on its mass. Large black holes, like those in the centers of galaxies, are incredibly cold, only fractions of a degree above absolute zero. But small black holes, if they exist, would be extremely hot. As a black hole evaporates through Hawking radiation and shrinks, its temperature rises. Eventually, if it becomes small enough, its temperature would approach the Planck temperature. In its final moments, a black hole becomes a furnace hotter than any star could ever be. Its last instant might resemble the first instant of the cosmos. This deep connection between black holes and the early universe suggests that the Planck temperature is not simply a number. It is a threshold marking a phase of reality itself, a point where quantum mechanics and gravity become inseparable. Both the Big Bang and black hole interiors are glimpses into this hidden phase. Yet our classical picture of a singularity, a point of infinite density, is almost certainly incomplete. Quantum mechanics forbids infinities of this sort. Instead, many physicists believe that singularities are regions where spacetime undergoes a phase transition, collapsing into something we do not yet have the mathematical tools to describe. Some theories propose that the center of a black hole might not be a point at all, but a region of extreme but finite density, perhaps with a small rebound or bounce, similar to how matter might behave under extreme pressures in early universe models. In loop quantum gravity, for example, spacetime is made of discrete loops, and these loops resist infinite compression. Instead of a singularity, they predict a tiny region of maximum density, a Planck core. At this core, temperature would approach the Planck scale. String theory offers a different picture. Instead of point-like particles, the theory envisions vibrating strings whose tension prevents infinite collapse. Black hole singularities might smear out into tiny stringy structures, again avoiding infinities. Another possibility is that black hole interiors link to other regions of spacetime through wormhole-like geometries, their cores replaced by bridges rather than points. In that case, the intense temperatures at the center would represent a transition zone rather than a terminal boundary. But regardless of the details, nearly all modern theories agree on one thing. The temperature in a black hole's core must rise toward the Planck scale because that temperature represents the limit at which spacetime can maintain coherence. Beyond it, the distinction between spacetime and matter dissolves. Black holes, then, are not cosmic oddities. They are windows into the deepest structure of the universe. They show us where our theories reach their limits. They remind us that the laws governing everyday life are fragile approximations of deeper truths hidden under extreme conditions. And they invite us to see the cosmos as a continuum, linking its smallest scales to its largest. The early universe, collapsing stars, quantum particles, all are part of the same story. All are shaped by the same fundamental constants. All are constrained by the same ultimate boundaries. As the black hole evaporates toward its final moment, its temperature climbs higher and higher, approaching the very limit that marked the universe's beginning. In that final instant, if our theories are correct, the black hole becomes a tiny echo of the Big Bang, a mirror held up to the earliest moment in cosmic history. Perhaps that echo is not simply resemblance. Perhaps the birth and death of the universe share the same physics. Perhaps singularities, whether at the beginning of time or in the heart of collapsing stars, are manifestations of the same underlying structure. And as we drift deeper into this reflection, a gentle question rises. If black holes can reach temperatures near the Planck scale, then what does this say about the nature of spacetime itself? What deeper laws must exist to govern the universe at these limits? In the next part, we explore that quest directly. The long search for a theory capable of describing gravity and quantum mechanics is one. Part 12. The role of quantum gravity. To truly describe what happens at the Planck temperature, scientists search for a theory that combines quantum mechanics and gravity. String theory, loop quantum gravity, and other frameworks attempt to paint a picture of this extreme frontier, where space is granular, time is discrete, and reality is woven from tiny vibrating structures. At ordinary conditions, quantum mechanics and general relativity coexist peacefully because they dominate different realms. Quantum mechanics rules the microscopic, electrons orbiting atoms, photons traveling in waves and packets, particles tunneling through barriers. General relativity rules the macroscopic, planets orbiting suns, galaxies twisting in spirals, the bending of starlight by massive clusters. Each theory excels precisely where the other becomes unnecessary. But near the Planck temperature, both quantum mechanics and gravity become equally powerful. Their domains overlap violently. Energy density becomes enormous. Space-time curves at tiny scales, and quantum fluctuations become so strong that they reshape the geometry they occur within. In this domain, neither quantum mechanics nor general relativity can work alone. They begin making contradictory predictions, each insisting on its own incomplete view of reality. Quantum gravity seeks to reconcile them, to build a single framework where spacetime and quantum fields arise from the same fundamental rules. This quest has been one of the great scientific pursuits of the last century. Not because of mathematical beauty alone, but because without such a theory, we cannot fully understand the universe's beginning, black hole interiors, or what lies beyond the Planck temperature. These extreme environments remain veiled to us, hidden by the limitations of our current equations. The earliest intuition about quantum gravity came from simple reasoning. If energy curves spacetime, and if energy exists in discrete packets, then spacetime must have a discrete structure too. It cannot be perfectly smooth. It must be built from tiny indivisible units, Planck-sized atoms of geometry. Loop quantum gravity is one attempt to formalize this idea. In this theory, spacetime is like a woven fabric of loops, each loop representing a quantum of area or volume. These loops form a vast network, constantly fluctuating and reshaping themselves. The geometry we experience, the smooth, continuous space we walk through, is merely the large-scale average of these microscopic loops. At the Planck scale, these loops jitter, stretch, shrink, and reconnect, producing the quantum foam we discussed earlier. In loop quantum gravity, the singularities predicted by relativity disappear. Spacetime cannot collapse to a zero-size point because the loops resist infinite compression. When a black hole collapses, or when the universe approaches the beginning of time, these quantum loops prevent a true singularity from forming. Instead, they produce a region of extremely high but finite density, a bounce rather than a breakdown. At this bounce, temperatures may approach the Planck scale, but they never reach infinity. String theory approaches the problem differently. Instead of treating particles as points, string theory imagines them as tiny one-dimensional strings vibrating at different frequencies. Each vibration corresponds to a different type of particle. A vibrating string in one mode becomes an electron, in another mode, a quark, in another, a photon. Intriguingly, one of the natural vibrations of these strings behaves like a particle that carries gravitational force, the graviton. This built-in graviton offers string theory a natural path toward quantum gravity. Gravity emerges not as a separate entity, but as one vibration among many. And because strings have finite length, they avoid the infinities that arise when point particles become too concentrated. At the Planck scale, the size of a string prevents spacetime from collapsing into a singularity. The strings stretch, vibrate, and smear out the energy, allowing gravity and quantum mechanics to coexist without contradiction. Even more fascinating is that string theory predicts additional dimensions beyond the familiar three of space and one of time. These hidden dimensions might be curled up at the Planck length, influencing physics without revealing themselves directly. Their presence could explain the relative weakness of gravity, as much of its influence may leak into these extra dimensions. Near the Planck temperature, these extra dimensions might unfurl or behave differently, contributing to the extreme behavior of spacetime. Another framework, known as causal dynamical triangulations, attempts to construct spacetime by piecing together tiny building blocks, four-dimensional triangles, that combine and rearrange themselves according to simple rules. Over time, these triangles generate large-scale geometry. Remarkably, simulations using this method have produced spacetimes that resemble ours, suggesting that complex universes can emerge from simple quantum ingredients. Other proposals include emergent spacetime theories, where spacetime itself is not fundamental, but arises from deeper quantum information structures. In these models, the universe behaves like a vast network of entangled quantum bits, and spacetime geometry emerges from the way these bits are connected. Time and distance become statistical outcomes rather than fundamental truths. At the Planck scale, the network becomes chaotic and reconfigures itself too frequently to define smooth geometry. Despite their differences, all quantum gravity theories share a few common themes. 1. Spacetime is not continuous. It is granular, composed of discrete units or structures that prevent infinite compression. 2. Time is not absolute. It may be quantized, emergent, or deeply intertwined with quantum processes. 3. Geometry is dynamic at microscopic scales. Distances and durations fluctuate constantly. 4. Singularities are not real. They represent the breakdown of classical equations, not physical infinities. 5. At the Planck temperature, all known physics transforms. Quantum gravity is not optional, it is required. These ideas help explain why classical general relativity fails near singularities and why quantum mechanics falters in the presence of strong curvature. They also explain why the Planck temperature marks a true boundary in nature. In the absence of quantum gravity, the early universe appears impossible, a place where infinities dominate and no coherent physical picture can form. But with quantum gravity, the story becomes smoother. Instead of a singular beginning, the universe may have emerged from a prior state. Instead of infinite temperature, there may have been a maximum density dictated by quantum geometry. Instead of time starting abruptly, it may have evolved from earlier configurations of quantum spacetime. Quantum gravity also influences our understanding of black holes. Instead of harboring singularities, black holes may contain regions of extreme but finite curvature. Instead of ending in infinite compression, collapsing matter may rebound in a new region of spacetime. Instead of information disappearing at the horizon, it may be preserved in the quantum structure of spacetime itself. In this way, quantum gravity is not just a mathematical pursuit. It is a lens through which we glimpse the universe as a unified whole. A universe where forces merge at high energy, where geometry and matter are two sides of the same coin, where time and space are emergent, and where the deepest truths are written not in infinities, but in the tiny, vibrating, fluctuating structures beneath them. And this brings us to a gentle but profound question. If quantum gravity governs the Planck scale, then why can't we reach these temperatures again? Why are they sealed away in the earliest universe? In the next part, we explore that quiet boundary, why the universe will never again climb to its maximum heat. Part 13. Why nothing can ever reach the Planck temperature. Again, the early universe reached these temperatures effortlessly because everything was compressed into an unimaginably tiny volume. Today, no star, no collision, and no explosion can achieve it. Even the most powerful particle accelerators fall short by factors of 1 trillion. The Planck temperature is a relic of the cosmos's birth, never to be recreated. To understand why the Planck temperature is forever out of reach, we must first return gently to what temperature means. Temperature is not simply heat in the everyday sense. It is the average energy of countless particles jostling, vibrating, and interacting. The more tightly they are packed together, the more intensely they scatter off one another, and the higher the energy density becomes. In the early universe, there were no vast stretches of emptiness like those we see today. Everything, every quantum field, every mode of radiation, every fluctuation was compressed into a space smaller than a proton. This compression forced energies to rise to unimaginable levels. It was not a matter of adding heat to a system, it was the unavoidable outcome of extreme confinement. When everything is squeezed together beyond the limits of ordinary geometry, temperature soars to the Planck scale naturally. But in the universe today, nothing is compressed enough to force such temperatures. Matter and energy are too diffuse, the cosmos is too large. Even the densest objects, neutron stars, black hole interiors, do not globally recreate the uniform, all-encompassing conditions that existed at the dawn of time. Even if we wanted to, we could not recreate the Planck temperature in a laboratory. The energy required would be so immense and the confinement so extreme that spacetime itself would crumble into quantum foam long before the temperature could rise to the necessary height. Instead of heating a small region further, we would collapse that region into a black hole or disrupt its geometry entirely. Nature itself enforces the limit. This reality becomes clearer when we consider our most advanced experiments. Particle accelerators like the Large Hadron Collider hurl protons into each other at incredible energies, reaching temperatures far hotter than the core of any star. For a fleeting moment, they recreate conditions similar to those that existed microseconds after the Big Bang, yet these temperatures are still trillions of times lower than the Planck scale. Not because we lack technological sophistication, but because the amount of energy required to reach the Planck temperature would need to be focused into a space so small that gravity would intervene. At a certain point, squeezing energy into a smaller region becomes impossible. The energy density becomes high enough that the region collapses into a tiny black hole. This sets a natural limit on temperature. If you try to go hotter than the Planck temperature, you do not get a more energetic system, you get gravitational collapse. This is not a technical limitation. It is a law of nature arising from the interplay between quantum mechanics, thermodynamics, and gravity. There's another reason the Planck temperature cannot be reached again: the expansion of the universe. As the cosmos expands, it cools. This cooling is not like a cup of tea left on a table. It is a fundamental dilution of energy density across space. Photons stretch to longer wavelengths, particles move apart. The average temperature of cosmic radiation drops over billions of years. Today, the universe's background temperature is only a few degrees above absolute zero. For the universe to return to the Planck temperature, it would need to contract by unimaginable proportions. It would have to reverse its expansion entirely, compressing all matter, all radiation, all dark energy back into a tiny volume. Current evidence suggests that the universe is not heading toward such a collapse. Instead, it is accelerating outward because of dark energy. The cosmos is drifting further from the Planck era with every passing moment. Another layer to this puzzle comes from the very nature of entropy. The early universe had extremely low entropy, an astonishing level of order compared to the complexity we see today. Low entropy is required for high temperature of the Planck kind. As entropy increases, the universe becomes more disordered and spread out. It loses the conditions needed to force extreme temperatures everywhere at once. The arrow of time itself, governed by the growth of entropy, pushes the universe further away from its initial state. This asymmetry means the universe can never return to the circumstances of its birth. The low entropy conditions that enabled the Planck temperature to arise existed only once. They were part of the starting configuration, not something that can be recreated. The cosmic deck has been dealt, and the cards have been played. Yet the inability to reach the Planck temperature is not a limitation. It is part of what makes our universe stable. If regions of space could easily reach such temperatures, spacetime would be prone to frequent collapse. Structures like atoms, stars, and galaxies would not survive. The universe would be perpetually turbulent, always on the brink of tearing itself apart. Instead, the Planck temperature sits like a boundary, marking the earliest chapter of cosmic history, separating a chaotic quantum gravitational storm from the calmer, structured universe we know. Still, the imprint of that era remains. The cosmic microwave background is a whisper from that cooling process. The distribution of galaxies carries the fingerprints of early fluctuations. Even the masses of particles and the strengths of forces may reflect events that unfolded as the universe dropped below the Planck scale. Modern physics teaches us that the Planck temperature is not only unreachable, it is unnecessary. The universe works because it left that temperature behind. Cooling allowed forces to separate. Cooling allowed atoms to form. Cooling allowed chemistry to arise, stars to ignite, planets to coalesce, and life to emerge. Every stage of cosmic evolution depends on distance from the Planck era. And yet, the boundary remains fascinating. It marks the point at which human understanding falters, where our physical theories stop agreeing, and where the universe's behavior becomes opaque. Physicists study the Planck temperature not because they expect to reach it, but because it illuminates the frontier of knowledge. It forces us to examine the limits of spacetime, the structure of quantum fields, and the origin of cosmic forces. In a sense, the Planck temperature is less a destination and more a compass. It points toward quantum gravity. It points toward a unified theory. It points toward the universe's earliest truth. But its role today is quiet, symbolic, unreachable by any technological means or natural process. Stars cannot reach it. Supernovae cannot reach it. Gamma-ray bursts cannot reach it. Even black hole evaporation stalls before it fully arrives. Only the Big Bang achieved the Planck temperature, and only because the universe itself was the confinement mechanism. This realization invites a gentle, reflective thought. We live in a universe whose beginning touched the limits of physics, but whose present drifts infinitely far from them. The Planck temperature is not simply a number, it is a memory of a world we can never revisit. And as the universe continues its cooling journey, another question arises. If the cosmos can never return to its maximum temperature, what prevents it from fracturing under the opposite extreme? Absolute cold. In the next part, we explore that quiet frontier, the balance between the universe's hottest moment and its coldest possible fate. Part 14. How cooling created everything we know. The moment the universe cooled below the Planck temperature, structure could finally form. Forces separated, space expanded smoothly, particles condensed. In the following milliseconds, the foundations for all chemistry, all physics, and every star were laid. Cooling, not heating, is what allowed the universe to become a home. To appreciate this, Imagine the universe as it existed at its maximum temperature, a storm of pure energy. No atoms, no particles with stable identity, no geometry that stayed still long enough to support motion or sequence. In that era, everything flickered chaotically. Space-time trembled, forces blended into one another, and temperatures soared so high that even the laws of physics blurred at the edges. Nothing resembling structure could exist there. No building blocks, no atoms, no beginnings. Cooling was not a loss. It was the first moment the universe could breathe. As the temperature dipped below the Planck scale, even by the smallest fraction, something remarkable began. Space-time calmed. Not entirely, there were still wild fluctuations, but the most extreme distortions faded. Quantum foam quieted. Regions of space stopped condensing and collapsing at random. Geometry stabilized enough for distance, direction, and time to take on meaning. This stability opened the door for forces to distinguish themselves. Physicists believe that at the Planck temperature, all fundamental forces may have been unified into a single interaction, one elegant but inaccessible rule from which all later physics descended. As the universe cooled, this unified force began to fracture, like crystal breaking into facets. First came gravity, separating from the others. Then, the strong nuclear force split away. Later, the electromagnetic and weak forces diverged from a shared identity. Cooling was the universe's act of differentiation. It created contrast, diversity, structure. As the universe expanded, cooling further, the wild fluctuations of energy began to shrink. The cosmos was still unimaginably hot, far hotter than any temperature we can reach today, but the order of events became clearer. Processes could unfold without being immediately torn apart. For the first time, interactions had room to evolve, and so, particles began to appear in forms that could persist. This happened in stages. At first came the simplest building blocks: quarks, electrons, neutrinos, and photons. Quarks darted frantically, colliding and separating and recombining, but the temperature was no longer so high that they immediately dissolved into the surrounding energy. They began to bond. The strong nuclear force, newly distinct, woven by gluons, pulled quarks into groups of 2 and 3. These clusters became the earliest protons and neutrons. In the same instant, matter and antimatter flooded the universe in equal measure. Cooling allowed them to exist long enough to interact in organized ways, to annihilate, to collide, to release energy, to leave behind slight imbalances. Those tiny asymmetries are the reason matter exists at all today. Without them, cooling would have created nothing more than a universe filled with light. But the temperature continued to fall. In the first microseconds, protons and neutrons began feeling the gravitational and strong forces in a way that allowed them to behave collectively. In mere fractions of a second, the early universe transformed from a chaotic plasma to a bath of particles with stable identities. These particles swam in a sea of radiation, interacting, bouncing, colliding. Out of these collisions emerged the first hints of structure, not atoms, but the ingredients from which atoms would later form. Cooling continued its quiet work. A few minutes after the Big Bang, the temperature dipped enough for nuclear fusion to begin. Protons and neutrons fused into the first atomic nuclei, simple ones like hydrogen, deuterium, and helium. For ordinary chemistry to emerge, electrons needed to bind to these nuclei, but the universe was still far too hot for that to happen. Photons carried enough energy to tear electrons away from anything they attempted to orbit, and so atoms remained incomplete. But the cooling never stopped. Hundreds of thousands of years later, the temperature finally fell to a point where electrons could attach themselves to nuclei without being ripped away. This process, called recombination, created the first stable atoms. Suddenly, the universe became transparent. Light could move without scattering. The cosmos that had once been a dense fog of radiation and charged particles became a vast, dark, silent expanse filled with neutral atoms. This shift marks the moment the universe truly began to resemble a place where structure was possible, where matter could clump, where gravity could sculpt. Cooling allowed gravity to take the stage more fully. Even as the universe expanded, Regions slightly denser than their surroundings began drawing in more material. These ripples, imprinted by quantum fluctuations in the earliest moments, grew into the first stars and galaxies. Over millions of years, collapsing clouds of hydrogen and helium ignited into the first stars, massive short-lived titans that burned brightly and died violently, producing heavier elements in their cores. Cooling made stars possible. Stars, in turn, made planets, carbon, oxygen, iron, the elements essential for life. As the universe continued its long descent into gentler temperatures, galaxies spun into spirals, clusters formed, dust accumulated, and planetary systems emerged from the ashes of ancient stars. Every stage that followed required temperatures far below the Planck limit. Structure thrives on calm, not chaos. Even today, cooling continues its slow work. The cosmic microwave background has stretched and cooled until it is barely above absolute zero. Stars warm their surroundings, but eventually cool as well. White dwarfs dim into black dwarfs. Galaxies exhaust their gas. Expansion continues. The cosmos moves toward greater emptiness, greater stillness. And yet, without the initial cooling, without the universe leaving behind its moment of maximum heat, none of this would exist. The galaxies overhead, the atoms in your body, the planets that orbit distant stars. Every pattern we see is a consequence of the universe drifting away from its hottest possible moment. The Planck temperature was the crucible in which the potential for physical laws formed. Cooling made those laws usable. Cooling allowed space to stretch smoothly. Cooling allowed forces to separate. Cooling allowed particles to persist. Cooling allowed atoms to bind. Cooling allowed stars to ignite. Cooling allowed life to emerge. It is a quiet but profound truth. The universe is built not on heat but on cooling. This understanding also reveals the fragility of the world we inhabit. The conditions that allowed structure to form required astonishing precision. If the universe had expanded too quickly, particles would never have formed atoms. If it had expanded too slowly, everything would have collapsed into black holes. But cooling occurred in a way that allowed balance, harmony, and structure to flourish. As you breathe in this present moment, you are experiencing the result of billions of years of gradual cooling, a process that began the instant the universe dipped below the Planck temperature. And from this gentle reflection arises a final question. If cooling created the universe we know, what quiet message does this offer about the future? About how the cosmos will continue to change as it grows colder still? In the next part, we drift into that final theme, the lessons the Planck temperature leaves for the fate of the universe. Part 15. What the Planck temperature reveals about reality. This, ultimate temperature, is more than a number. It is a boundary etched into the laws of the cosmos, a reminder that even the universe has limits, a clue that space and time emerge from deeper rules we have not yet fully uncovered, and a whisper from the universe's first moment, telling us that creation began not in order, but in fire. To sit with the idea of the Planck temperature is to sit at the edge of human understanding. Every scientific concept we rely on, particles, fields, forces, spacetime geometry, begins to dissolve when confronted with this threshold. The Planck temperature marks the point where our theories do not merely struggle, but fail. It is the edge of the map, the boundary where the known meets the unknowable. But the Planck temperature is not just a wall, it is a signpost. It points back to where we came from and forward to what we do not yet understand. To grasp its significance, imagine the universe as a vast story written in the language of physics. For most of that story, the language is clear. Forces behave predictably. Particles follow rules. Energy flows along understandable paths. But at the very beginning, the opening sentence, the language breaks down. The ink blurs. The letters fold into one another. The story begins in a script we cannot yet read. The Planck temperature marks the edge of that blurred beginning. It tells us that physics, as we know it, is incomplete, not broken, but unfinished. It reveals three profound truths. First, the universe has limits. Not everything can rise indefinitely. Not every question has a classical answer. Temperature cannot exceed the Planck scale any more than velocity can exceed the speed of light. These limits are not restrictions, they are anchors, signs that reality is governed by principles deeper than chaos, deeper than freedom without structure. The limit tells us that the universe is not arbitrary, it is shaped by constants woven into its foundation. Second, spacetime is not fundamental. The Planck temperature forces us to confront a difficult but increasingly necessary idea. Space and time may not be the bedrock of reality. They may be emergent, arising from deeper processes, just as heat emerges from the random motion of molecules. Near the Planck temperature, spacetime shudders into uncertainty. Distances cannot be measured, durations cannot be defined, geometry becomes fluid. This suggests that below the Planck scale lies a domain where space and time have no conventional meaning, a place where reality is built from something more primitive, information, loops, vibrating strings, quantum networks, or structures yet unimagined. The Planck temperature is the gateway to this deeper layer. Third, the universe began not in order, but in fire. The first moment of existence was not calm. It was not organized, not predictable, not stable. It was heat so intense that space-time writhed, forces merged, particles could not exist, time had no direction. What we call the beginning was not a peaceful origin, but a storm. A furnace of maximum energy density where reality struggled to form. This reminds us that order is an achievement, not a default state. The universe we know had to cool, had to expand, had to calm itself before any structure could arise. Everything we recognize, from atoms to galaxies to life, emerged because the cosmos escaped the Planck temperature. But perhaps the most important lesson is this. The Planck temperature reveals that there is a deeper layer of physics waiting to be discovered. Einstein taught us that space and time are intertwined. Quantum mechanics showed us that particles are clouds of probability. The Planck temperature tells us these two perspectives are incomplete pieces of a single story. It is the point where quantum mechanics and general relativity collide, where uncertainty meets curvature, where probability meets geometry. Our current theories offer hints. String theory whispers that particles are vibrations of deeper structures. Loop quantum gravity hints that space is woven from discrete loops. Holographic principles suggest spacetime may arise from quantum information encoded at boundaries. Causal set theory proposes that the universe is built from sequences of discrete events. Each of these frameworks points toward the same truth. Reality is richer than our current mathematics can express. The Planck temperature is the place where these deeper structures must reveal themselves. It is not just a number, it is an invitation. It reminds us that the universe, for all its grandeur, is not static. It is unfolding. It is a puzzle with pieces still missing. Its most extreme boundaries, its highest temperature, its smallest length, its shortest time, are clues left behind by creation itself. The Planck temperature tells us that there was once a moment when the universe was too energetic for the laws we now rely on. It hints that our universe may have passed through phases of existence we cannot yet describe. It implies that new physics is not hidden in distant galaxies or exotic materials, but is embedded in the very beginning of time. But there is another, more reflective layer to this boundary. The Planck temperature reminds us that the universe is not infinitely malleable. It is shaped by constraints. Its evolution depends not only on what is possible, but on what is impossible. Without limits, structure would not arise. Without cooling, complexity would never unfold. Without boundaries, there would be no meaning to motion, no contrast in temperature, no formation of matter. Limits are not obstructions, they are the scaffolding from which reality is built. And there is a quiet beauty in this. The same boundary that makes the earliest universe unknowable also makes the present universe possible. The same heat that once tore spacetime apart allowed spacetime to eventually settle. The same limit that prevents us from reaching the Planck temperature protects the universe from collapsing into instability. Every boundary in physics carries this dual nature. It restricts and it defines. It prevents and it enables. In the deep quiet beyond thought, the Planck temperature stands as a reminder that reality is a balance between chaos and order, between fire and form, between the infinite and the finite. It tells us that creation began at the very edge of comprehension, in a place where time faltered and space flickered, a place we may never fully map, but toward which our understanding continues to drift. And as we linger at this threshold, one final gentle thought settles in. The universe carries its origins not as a place we can return to, but as a pattern woven into everything that exists. Every atom, every photon, every breath you take is a descendant of that incandescent moment. The Planck temperature is the universe's reminder of where it came from, and a whisper of how much more there is left to understand.